Hi everyone. It's my pleasure to introduce Raveena Khan, who is an integrated MTech PhD student at the Indian Institute of Astrophysics in Bangalore, and a former Newkirk Fellow at the High Altitude Observatory in Colorado. She's currently visiting the CfA to work with Dr. Christopher Moore on characterization of CMOS detectors for X-ray photon detection. She specializes in spectropolarimetric instrumentation and techniques in extreme UV for diagnosing the electromagnetic fields at the solar corona. And her research interests also include numerical modeling of coronal emission lines, optical design, and optimization of astronomical instruments. All right, Raveena, we're very happy to have you here, and take it away.
Thank you all for the introduction, and thank you for the opportunity to for me to present in front of you all. So I'll give this is a overview of my talk. I'll explain the different polarization states and the importance of measuring coronal magnetic fields, and what are the magnetic field diagnostic techniques that are used so far, like to such as Zeeman effect and Hanle effect, and then I'll describe the identified new coronal emission lines which are sensitive to the Hanle effect, and then with one of the lines, that is neon 8770 angstrom, like we model the polarization, how it varies across the different phases of solar cycle. I'll talk about that, and with this signal levels, what is the required polarization sensitivity for future instruments to be able to detect such signals. And finally, I'll discuss more on the Hanle effect and its future prospects. So recalling the how the different states of polarization can be represented, it basically requires like Stokes parameters IQ and U, IQ, U, and V. So taking a reference X and Y, Stokes U can be represented if the electric field vibration is along the X-axis, or which is represented as Stokes plus Q, and if it's along Y-axis, then it's represented as minus Q. And if the vibration is along at 45-degree to the reference axis X, then we call it as plus U, and at minus 45 it's called minus U. And similarly, if the oscillations are circular along the line of sight, then we either call it as right circular polarization if it's rotating anticlockwise, and or it's a left circular polarization the other way. So this is a basic optical setup, how to generate linear polarization, Stokes Q and U. So basically, if we have a wide grid polarizer with windows etched along a particular direction, and we let the unpolarized light pass through it, then the output will be linearly polarized along this particular axis. And similarly, if we rotate the polarizer at angle theta, then we'll get a component cos theta of this component E naught. Similarly, to produce circular polarization, we keep a quarter wave plate just after the linear polarizer to produce circularly polarized light. So now coming to the importance of measuring coronal magnetic fields, it's a key ingredient to understand several phenomena such as acceleration of solar wind, formation and evaluation of features like filaments, coronal loops, streamers, and ultimately the explosion of energy and particles in form of flares and coronal mass ejections, which thereby interact with the Earth's outer atmosphere, interfering with GPS satellite and satellite electronics, etc. So we usually study the sun using the light that we collect with our telescope. That means by analyzing the electromagnetic radiation coming from the sun, we can obtain empirical information on the different layers of the solar atmosphere, like measuring the velocity, density, temperatures, etc. But then, how do we measure the magnetic fields using the same light that we collect? So the most commonly used diagnostic method is the Zeeman effect, which is the splitting of energy levels in the presence of an external magnetic field. So basically, instead of a single spectral line, we are able to get like multiple spectral components. And if we can measure the separation between the either of the spectral components and use this approximate formula, then we can derive the total magnetic field strength. So to visualize how it looks like, so this is a sunspot image that was observed by Machmet Pierce solar facility on Kitt Peak, and this basically and alongside is the spectra where we can see that the iron 1 line is getting split into three spectral components inside the sunspot where the magnetic fields are very strong. Whereas outside the sunspot where the magnetic fields are weaker, we can barely see any splitting. Rather, we see that the spectral line is slightly broadened. So in such weak field regions where the Zeeman splitting is very weak, we can use like there is this resonance scattering due to the incoming anisotropic radiation, which comes into picture, and it can play a role and help us in understanding the weak field regions. So to explain what is the resonance scattering and how Hanle effect comes into picture here. So let's say we consider this atomic system with lower level J angular momentum 0 and upper level angular momentum as 1. So the when the anisotropic radiation beam coming from the underlying layers is incident on this particular atomic system, which is suspended in the corona, it creates this population imbalance in the magnetic sublevels. And this is called the atomic polarization. So basically, there is a net creation of angular momentum, because of which, when the anisotropic radiation is getting scattered from this atomic system, the scattered radiation is linearly polarized. Now, when the separation between these magnetic sublevels is comparable to the natural width of the energy level, what happens here in the presence of a weak magnetic field, the this atomic polarization that was earlier induced by the anisotropic radiation, that gets modified. And this effect is called the Hanle effect. So, but how do we identify such atomic systems which are sensitive to the Hanle effect for a particular region to use that particular atomic system for probing the magnetic fields? So for that, we need to calculate this particular factor, G omega tau, where G is the Landesi factor of upper energy level, omega is the Larmor frequency, and tau is the lifetime of the upper energy level, which is basically the inverse of the summation of Einstein A coefficient. So if we calculate this factor, and we for a particular line transition, and we see that the this factor lies within this range, then we can theoretically say that okay, we can use that particular line transition for probing the field strengths expected in a particular region. Now, to make things simpler, what we do is we calculate the field strength corresponding to this factor being 1, which is called the critical Hanle field, so that we don't have to say always a range, but we can just talk about this critical Hanle field. And in case of corona, like the expected field strengths are in the order of a few milligauss to 200 to 300 gauss. So that's the kind of critical Hanle field we want for using a particular spectral line for magnetometry. So there is another parameter which is important, That's the polarizability coefficient, which is basically a scaling factor that quantifies or tells us the fraction of maximum linear polarization that can be attained for a given line transition due to the resonance scattering of the incoming anisotropic radiation. Now, for this particular case, we can uh, use these analytical expressions for deriving the coefficient, and this corresponds to the transition, three allowed transitions, delta J equals to 0 plus minus 1. And so when we were doing the literature survey and we came across the summer spectroscopic observations, we found that there are plenty of emission lines being emitted from the corona in the UV and FUV wavelength range. So, and if we compare the sun, like this is observed by SDO in the leftmost image shows in 171 angstrom, which is in the EUV, whereas the rightmost image is in the visible at 4500 angstrom. So we can see how structured is the corona that we can look at in the EUV. So we went ahead and collected data from these three space-based instruments to cover a wavelength range starting from 100 angstrom to about 1600 angstrom, covering a wave temperature range of 10 to the power 5.5 to 10 to the power 6.3 Kelvin, which is the typical temperature range of corona. And we calculated the parameters, critical Hanle field, polarizability coefficient, and Einstein A coefficient. And this is a part of the very lengthy table that we published in the 2022 paper. And so in this, I want to point out two important factors, critical Hanle field. So if you notice, for all these transitions, the critical Hanle field is very high, like greater than 1000 Gauss. So that means these particular lines cannot be used for diagnosing the coronal magnetic fields, which are in the order of few Gauss. But these lines may be used for tracking the field orientation in the plane of sky. And next is the W2 coefficient. We can see there are two lines here which have W2 equals to 0. So that means these lines cannot hold the atomic polarization no matter how polarized the incoming radiation is. So the entire paper can be found in this link. So out of all the lines that for which we calculated those parameters, we selected only those lines based on these three criteria, which is taking a range of critical Hanle field from 10 milligauss to 200 Gauss, and lines which have polarizability coefficient greater than 0 and which have a good enough line radiance. And based on these three criteria, we were able to select a handful of lines which are shown in this representative way. And so in this representation, basically the width of each rectangular box along the x-axis represents the approximate range of line formation temperature of that particular line, and along the y-axis, the width represents the Hanle sensitivity domain. So now that we have the list of potential UV lines, how do we know what is the polarization signal that we expect in any of these wavelengths? So for that, we chose the neon 8 line at 770 angstrom for further modeling. And there are several reasons for that. So it has a critical Hanle field of 49 Gauss. Polarizability coefficient is 0.5. It corresponds to an electric dipole transition with very high Einstein A coefficient. That means the line transition happens very fast before the collisions can actually destroy its atomic polarization. And then line radiance is about 40 units. In fact, it is the brightest line after the oxygen 6 line at 1032 angstrom, which has been very widely and extensively studied so far. And then its line formation temperature is around 600,000 to 800,000 Kelvin. Which indicates that it originates from the transition region of the lower corona. So for further modeling Neon 8, we use forward codes, and this is a graphical user interface of forward. And in the past couple of years, we were able to extend its spectropolarimetric capability into the EUV regime. So in case of Neon 8, we incorporated like assumed a two-level atomic model for Neon 8 because Neon 8 is a resonance line, so it's a very good approximation to consider. And for the source intensity, which is basically the source of pumping radiation, for that we use the average Poisson radiation from the summer spectroscopic observations. And for the physical state model, we used the MHD model developed by PSI. So PSI mass, it's a 3D MHD code, and it basically uses measurements of photospheric magnetic field vector from HMI as the primary boundary condition, and then solves the MHD equations in spherical coordinates. And it basically gives us and the ground truth information of coronal plasma conditions. And so far, it has been able to predict the conditions of the solar corona prior to the solar eclipse. And so, this is a very good model to start with. And this is an example of a slice of the temperature map, how it looks like. So now that we have the source intensity, atmospheric model, and atomic model in forward, we calculated the scattered intensity, which is Stokes I, Q, and U, by integrating the emission coefficients epsilon I along the line of sight. So this is a basic crude geometry. And so in this study, what our motive was to study the global change of the polarization across the different phases of the solar cycle. So so these are the years that we chose, and because our motive was to just see the global change, so we chose the corresponding Carrington rotation in the month of December of each of these years. So that's why you see a discontinuity in the numbers of the Carrington rotation. And Carrington rotation is a system of numbering the sun's one complete rotation about its axis. So, and this system began in 1853. So currently we are at 2295 Carrington rotation of the sun. So yeah, so this is the whole cycle that we have covered for modeling and simulating the polarization. And also in this study, so we not only included the effect of magnetic field due to Hanle effect, but we also studied the effect of electron collisions, which is very important at the lower corona where the electron density is very high and can lead to depolarization of the emitted radiation completely. So the leftmost image is the temperature maps and the rightmost is the Stokes I maps. And we can see as we proceed into the maxima phase, the intensity increases and then gradually drops as we go to reach the minima phase. So here is a still image of the comparing the maxima and the minima phase. Next, we calculated the polarization angle of the or the direction angle of the polarization vector. And to begin with, we first consider the define the reference axis that we want to consider before talking about whether the polarization vectors are rotating clockwise or anti-clockwise. So basically, first we chose the tangent to the limb as the direction where the scattering polarization is maximum, which is in the absence of any magnetic field in the model. So this is the direction that we choose for as the reference axis. And then as we switch on the magnetic field, we start to see this red and blue patches. And if we compare between the maxima and the minima phase, we can see that the red regions are more pronounced here as compared to the minima phase, where we can barely see the red and blue regions at the poles. So this is again to show the temporal changes along the different phases of the solar cycle, and we can see how these patches are becoming more pronounced at the maxima phase and then gradually becoming almost near the reference axis as we go to the minima. Then we calculated the degree of total linear polarization, which is L over I, and where L is the root sum square of Stokes Q and U, and the denominator I is Stokes I, which is the sum of both polarized and unpolarized intensity. So here we can see the off-limb features, like how it changes with different phases of the solar cycle, and we can clearly see that the electron density, as it drops very drastically off the limb as we go to higher layers, the signal increases at towards 2 solar radii. And this effect, I'll show in the later slide. It's kind of very prominent during the maxima and minima phase, how the structure changes. And on the disk, there is a very interesting feature due to the Hanle effect that I'll explain here. So if you see, so scattering polarization is maximum at 90 degrees scattering, when the scattered radiation is coming at 90 degree to the incident radiation. Whereas it becomes minimum if the direction of the scattered radiation is along the incident radiation, because of which we can see that at the limb the signals are maximum, as we move towards the disk center, the signals become minimum. However, at the center, as we reach to the maximum phase where we see more complex magnetic field structures, we can see that the minima at the disk center is getting shifted, or it's no longer minima, but we can see that there is positive polarization. That's because of the inclined magnetic fields or more complex magnetic field structures, because of which this symmetry is getting broken. So yeah, so this is a still image showing the difference between the maxima and minima phase. So in the minima, we can see a more dipolar structure, because there is less in this phase we can like closely approximate the sun as a dipole model, whereas in during the maxima phase we see there are so many structures around. So now that okay, yeah, I forgot to mention the scale. So the scale is in the log. So in this, we can see in the off limb, we can see that the signals are changing from 10 to the minus 4 at the lower corona to about 10% at 2 solar radii. Whereas here on the disk, we see that the signal levels are in the order of 10 to the minus 6 at the disk center to 10 to the minus 4 at the limb. Yeah, so now that we know the signal levels, let's say we want to measure 10 to the minus 4 signal levels, then what is the polarization sensitivity we suggest on, or we require for future instruments to detect these signals? And to derive that, we use this equation, which can be derived through the error propagation in the linear polarization L over I, which here is represented as capital P. So here sigma I is the noise associated with the Stokes I, the total intensity. Epsilon I is the efficiency for measuring Stokes I, and epsilon Q and U are the efficiencies for Stokes Q and U. So using this equation, we simulated for different telescope apertures how the polarization sensitivity changes for the maxima and minima period. For this study, we chose solar cycle 23. So the red dashed lines represent the minima phase, and the blue solid lines represent the sensitivity is required during the maxima phase. And in this study, we also considered like different spatial samplings and how that changes the sensitivity. So we can see that to reach better than 10 to the minus 4 signals, we need to go to higher spatial samplings, maybe better than 6.4 arcsecond per pixel. And like that would be enough for the maxima phase. But if we want to observe or do polarimetry during the minima phase, we have to go maybe up to 32 arcsecond per pixel spatial sampling. And these sensitivity, so these were done for an integration time of 10 minutes. And this sensitivity levels can further be improved if we go to longer integration times, which we can see here. So I'll finally end my talk with this final slide explaining on the future prospects and potential of Hanle effect in UV. So we have known that Hanle effect is much more sensitive to much weaker magnetic fields in the order of a few Gauss compared to the Zeeman effect, and therefore magnetic fields in the atmosphere of transiting exoplanets will help us understand how they interact with the high energy particles in the host stellar wind, and that will help us to understand the planet's longevity or the habitability. And in case of Jupiter or Jupiter-like planets, in in this reference, they have seen that the strongest or the brightest emission line is the Lyman alpha line at 1215 angstrom, which is an FUV line. And this particular line is very sensitive to the coronal magnetic fields in the order of a few tens of Gauss. So observing the polarization in this emission line will help us to measure the magnetic fields in the thermosphere and the coronal layers of the Jupiter and Jupiter-like planets. And then further, electric dipole transitions like the neon 8 line, which is in principle sensitive to both the magnetic field strength and orientation, it can be used to study the magnetic field topology and strength, not only at the solar outermost layers, but also for studying the magnetic fields at the stellar corona. And finally, Hanle effect as a diagnostic of magnetic fields in hot stellar envelopes can also help in understanding the stellar wind expansion.
Do we have questions in the room or in the room? In the meantime, I have a question. You showed the the comparison of the beautiful UV sun and optical sun. It was relatively far in the beginning. And yeah, one can really see very nicely how many features there are in the UV. And in the optical image, there is this kind of this feature here.
Yeah.
Is that real or what?
That's an artifact actually. This is a raw image. It's not been processed. So J-Helio Viewer is the software which I use to grab this image. Yeah.
Okay. Do you have any further questions? Yes.
Maybe it's a naive question. At the very end of your talk, you mentioned that the best line for probing exoplanets, for instance, is Lyman alpha. But how do you envisage this practically? Because in the near Earth orbit, you have Lyman alpha from geocorona, and it basically outshines everything. And I'm not sure whether it will be substantially better, but I mean, better to the sensitivity, better to the levels that you will be able to reach sensitivities to detect it in exoplanets, even if you move to L2 or a little bit further away from the Earth. Do you have any comments on this?
Actually, that was a that was for the Jupiter, like, it was, the observation was in Jupiter, around the Jupiter
Okay.
atmosphere. Yes, this same issue we do have for Sun also, like using Lyman alpha. That's why, like, we are looking for more lines in UV, which is shorter than the Lyman alpha line. Yeah, but that was just an example. Like, people have seen Lyman alpha emission to be very strong in the atmosphere of Jupiter, but there may be other lines too in the UV.
All right. Unless there are any further questions, like, let's thank Raveena again. And as a reminder, next week we will be in P108. That is next to the Wolfach library.
Next slide, please.